Hi there. In today's lecture video, we are going to be continuing with differential equations, and we're going to be looking at first-order linear differential equations. So this is another type of differential equation that you can add to the list that we looked at last time. And like those ones that we looked at last time, there is a special form for the right-hand side of the differential equation. So we have dy by dx is equal to f of xy. So this is what we had in general, and then we looked at specific cases of what this right-hand side looks like. We're going to continue that today by looking at f of xy in the form of q of x minus p of x times y. Okay, so this is just another form of the right-hand side that if it has this form, we have a method that we can use to solve this equation. Now, instead of writing it like this, usually we write it as dy by dx plus p of xy is equal to q of x. Okay, this is typically the standard form for the differential equation. Okay, so how do we solve something like this? So what we do is we look at the left-hand side and we try and combine these two terms into a single term. So we know that with the product rule, if we have something like d by dx of f times g, then we get the derivative of the first one, we leave the second one alone, plus we leave the first one alone, take the derivative of the second. So we end up with a combination of two terms with alternating derivatives. Okay, we want to try to do something like that with this. So we see we've got dy by dx for the first term, and then we got y for the second term. We want to try to combine these in a way. So what we do is we use what's called an integrating factor. So we use an integrating factor. Okay, sometimes it's called I of x, sometimes it's called mu of x. Okay, so we use an integrating factor to combine the left-hand side into a single term. Okay. So I'll just write out what the integrating factor is and then go over how we get there. So the integrating factor mu is equal to e to the integral p of x dx. Okay, so that's our integrating factor. We define this new function mu to be e to the power integral p of x dx, where p of x is that function in front of the y term. Okay, so how do we use this? Well, with this integrating factor, we can rewrite this equation. Okay, so dy by dx plus p of xy equals q of x. We can rewrite it as d by dx of y of x times mu of x is equal to mu of x times q of x. Okay. Now, using the fundamental theorem of calculus, we can just integrate both sides. The integral and the derivative will cancel. So we're left with y of x times mu of x is equal to the integral of mu of x times q of x dx plus c. Then we can divide through by mu of x, and we get y of x is equal to 1 over mu of x integral of mu of x q of x plus c. Okay, we end up with this as our solution using this integrating factor. Okay, so this is the method that we use. Okay, so once we know our integrating factor, we can just substitute it in and we can get our solution. Okay, but how does this integrating factor come to be? Okay, so let's just look at the our original function. So we have original differential equation. So dy by dx plus p of x y is equal to q of x. Okay, what we want to do now is multiply through by mu of x. So we're going to have mu of x times dy by dx plus p of x y is equal to mu of x. Okay, so we just multiply through both sides by that, so times q of x. Okay, then we can distribute that, so we get mu of x dy by dx plus mu of x p of x y is equal to, again, mu of x q of x. Okay, and like I said before, we want to combine these two sides into a single term. Now notice that this looks fairly similar to the product rule. So here we've got mu times dy by dx plus something else times y. If there's something else here, the mu of x p prime of x, if we can make this be equal to d mu by dx, so if we force this to be true, then this left-hand side is just the product rule after taking the derivative. So if we can force this to be true, then we get d by dx of mu of x times p of x is equal to mu of x times q of x, which is what we had before. So what we want is this mu of x times p of x to be equal to d mu by dx. If we can do that, then we can write this left-hand side as a single term. So we want mu of x times p of x to be equal to, so we want this to be true, d mu by dx. So now we have a simple differential equation for mu of x. Okay, so now this is another differential equation, but we see that it is separable. So we learned that last time. So we can write this as 1 over mu of x, or we can write it as 1 over mu, that will be a bit clearer. D mu is equal to 1 over, p of x dx. Okay, so we just multiply both sides there by dx and then take the mu across. Now we can integrate both sides. Okay, so we get the natural log of mu is equal to the integral p of x dx. Okay, usually we have a plus c, but we can leave that out, and we'll see now. So let's see what happens if we do add a plus c, and then we'll see that we don't actually need to put that in. Okay, we can undo the logarithm with exponentiation, so we have mu of x is equal to e to the integral p of x dx plus c, and then the plus c in the exponent there, we can separate that out to be a multiplicative constant. So we can have mu of x is equal to e to the c times e to the integral p of x dx. Okay, c is a constant, so e to the c is a constant. Let's call that a. So we have mu of x equals a times e to the integral p of x dx. Okay, so we have this integrating factor mu with a constant in front. Now I said that the constant doesn't matter, and the reason for that is that when we substitute mu, let's go back here to the previous statement, so we substitute mu, we see that it appears on the left-hand side and the right-hand side. So any constant that we put, so let's say we have our a times mu, that constant will appear on the left and on the right. So whatever the constant is, we can just cancel it out. Okay, like that. Oops. There we go. Okay, so the constant on both sides, we can always just cancel it. So here, for this constant, we can get rid of it. Okay, so our integrating factor we can write without the constant. Okay, and again, once we have our integrating factor mu, we can substitute it back in to this equation here, and we can get our solution. Okay, let's have a look at an example of this. Okay, so example. Okay, so we have xy prime minus 2y is equal to x squared. Now this is not in standard form. We don't have p of x times y equals q of x. We don't have those terms here. We've got an x times dy by dx instead. We don't want that. So let's first divide through by x. So we have y prime minus 2 over xy is equal to x. Okay, now this is in our standard form. So this is y prime plus p of xy is equal to q of x. We can see that p of x is going to be minus 2 over x, and q of x, that's just x. So now that we've identified our terms, we can use our integrating factor. So mu of x will be e to the integral p of x dx. So that's going to be e to the integral minus 2 over x dx. That will be e to the minus 2 natural log of x. Okay, we can take the minus 2 inside the logarithm there, so we end up with 1 over x squared. So that's going to be our integrating factor. So now we can substitute that into that previous equation. So d by dx, our integrating factor times y is equal to the integrating factor times q. Okay, but q, that was just x. So we have d by dx of 1 over x squared times y is equal to 1 over x. Okay, x over x squared, that's 1 over x. Now we can integrate both sides. So we get 1 over x squared times y is equal to the integral 1 over x dx. So that's going to be the natural log of x plus c. Okay, don't forget your constant plus c. Now we can solve for y. So y will then be equal to x squared natural log of x plus c times x squared. So we get our family of solutions. If we were given some initial condition, then this would be an initial value problem, and so we could solve for that specific value of c. But in this case, we don't have an initial condition, so we can just leave our answer like this. Okay. For more problems to go through, please look at the tutorial 4, exercise 9.5. Okay, so those are all the practice problems for this linear differential equations. Okay, so we're going to leave it at that for today. Pretty short lecture just to go through this. Please go through those practice problems. Okay, so once you understand the method, most of the work then becomes practicing these problems. Okay, so there's not much to understand with all of this theory here. So the main part is to do these problems and learn the method. Okay, if you have any questions, please just send me an email. I'll be happy to help. Or you can email the tutors. Okay, they're also available to help. And then they will also be available on Thursday during the tutorial period times. Okay, so you can send them questions on the tutorial WhatsApp groups. Okay, and then they can help you out there. Okay, but please, if you have any issues, please just email me or the tutors so that we can help you out. And do the tutorial problems. It's very good practice. Okay, so just understanding the method, that's not enough. You need to do the problems for practice. Okay, I'll see you next time.